Hi everyone, welcome to NDC Sydney. It's so good. I am a little bit excited that we're actually doing this in person for a change. Has anyone been to an in-person conference since the dark ages before COVID? Yep, okay, good. So I think this is a great chance for us all to connect and meet each other. Hopefully when you're in between sessions, you do the nerdy introvert thing of making sure you don't talk to anyone. You just kind of stand near other people and look like that. That said, feel free to come up and talk to me anytime at all. I'm quite happy to have a chat to anyone. If there's questions coming out from this talk as well, or you're interested in a job with Willow, sorry, got to do that sort of thing. I am happy to talk. My name is Richard Banks. You can see it on the screen there. I'm not going to talk about myself other than to say I am a distinguished engineer at Willow, and distinguished just means old, apparently. So that's why the grey hair or the lack of. And I was one of those people who put their hands up for more than 20 years doing something. It's like, you can't tell, right? I look like I'm 18, it's great. When we're talking, this is a talk about performance, by the way, before I move on to the next slide. You probably figured that out from the name, hopefully. But the intent of this talk is really driven by what we've seen in the .NET space over the last 3-4 releases now, 5, from basically full framework to .NET Core 2 was kind of like, let's make it work. And then at 3, Microsoft went, let's make this thing bloody fast. And then they made it faster, and then they skipped 4 and went to 5. And that got faster again, and then 6 has become faster again, and with 7 there's even more work. And I don't know if any of you have had a look at some of the posts coming out of Microsoft recently around the performance improvements that happen within the framework itself, and the low-level detail they go to explain how they've optimized code that is in hot paths so that everyone using the framework gets lifted up by those changes. And you look at it and you go through the details, it's like, bloody hell, how do I do this? This is kind of propeller head stuff. What I wanted to do is take the idea and the process of performance improvement and figure out how we can apply it to our own code, so that performance improvements is something that we can all adopt and all benefit from, and that it's not the inner workings of a .NET framework that give us performance, but it's just going through the steps of what's there. So this is effectively going to be a walkthrough of a library, which I will give you the name of in a little bit, explaining how the process works, what we want to be thinking about, and going from there. Now, the obvious tip for any type of performance improvements, the primary goal is very simple. I know, genius. That's why I'm standing up the front and you're not. Do less, and that's a great tip, and at that point we could just stop the talk here and we're done because we've done less. In reality, is less what, right? So less I/O is the obvious thing. For most of our applications, we're not doing frameworks. We're not doing a lot of CPU stuff. Most of our applications are going to be doing less I/O. The classic N+1 calls to databases. Has anyone other than me done that? Or you're just liars? Okay, all right, the second one, got it. Less I/O is really important, even just the amount of things. You might make the same number of calls, but if you reduce your bandwidth, you will get better performance because you're sending less data. Less I/O to disk, all these sort of operations. Any CPU improvements and performance improvements at a CPU level are going to be dwarfed by the improvements that you can make in terms of I/O. I don't know if you've seen this at all. I ran across this years ago. It's the idea of if we take I/O or compute latency and expand that to human scale, what happens? So if we consider one CPU cycle is 1 human second, I like some of the numbers here. For example, memory access is about 4 minutes, so I can save something to memory or do a memory operation in 4 minutes. So I'll get back to you. Just sit around and wait. It's not very exciting. Or we get right down the bottom, using the internet, send a message between San Francisco and New York. 5 years. Now the obvious thing is, if that was real, then what did you do at work today, dear? I'm still sending that packet. I'll get back to you in 5 years' time. The boss is going to be like, oh, good job, well done, you get a raise. But of course, we're in Australia. Our internet is so much better than that, right? Sydney to New York, anyone want to guess? 30 years maybe, something like that at human scale. So what did you do in your career? I sent a message to New York. Oh, the best. And if we think about that, you can see the performance improvements from an I/O perspective versus CPU and everything else. It's just chalk and cheese. So always focus on performance around I/O first. So that's why I have it top, and that's why it's the red line item there. Beyond that, we have thread blocking, anything that's going to block execution, garbage collector, classic example. This is why async and await has become so popular in recent times, because we can start doing more things while threads are waiting for I/O to complete and the like. So we want to keep on top of that. You can overdo it. I had some code I was looking at a little while ago, and I didn't write it, which is unusual, where we basically took a piece of work and spread it across multiple threads. So many threads that we starved the thread pool. Good job, because we didn't think about maximums, and we just made the whole application worse, because then we've got overheads of thread creation and we're all sitting around waiting for a turn. No one's getting anything, but it's multi-threaded. Why is it not working? That's, again, just my experience, right? No one else has done that? Okay, good. Yeah. All right, well, I'm going to learn from you guys. And the last one being CPU. There, obviously, everything at the end of the day runs with CPU. We want to focus on that as well, but it is third in the hierarchy of what we normally think about. This is where also memory allocation comes into play. Memory allocation drives CPU load. You have to allocate the memory. You have to deallocate it. You have to keep track of it. It's all CPU time. And there are other benefits around improving performance from a CPU perspective, such as heat generation, something we need to consider. Green computing initiatives, heat generation, energy consumption. If I use less CPU, I'm using less energy. And given where we're at with energy these days and the impending energy crisis thanks to electric cars and everything else that's going to occur, guaranteed. And you should probably jump to, I think Richard Campbell's doing a talk on this later tomorrow. Might be worth going to. A lot of that is going to be really important for us, that green computing initiatives that are happening will end up impacting our industry, and we will have to pay attention to it. So performance improvement is valuable from that perspective. All right, so that's the preamble. The way I think about performance, as you can see, I treat it like detective work. I don't want to say I'm Sherlock Holmes, because I'm not. But I do like that idea of there is a problem, I'm trying to discover what the problem is. I'm trying to find the root cause of what's going on. And then I'm going to problem solve that thing. So not only do I find the culprit and go, aha, Watson, but I'm also then going to take that culprit and beat the crap out of them, so to speak. I'm not incurring violence in the room at all. But to then improve that situation and make things better. So it's kind of cool. I like puzzle solving. It's great fun. I like the idea of investigating, so I enjoy this sort of work. Now, there are some prerequisites before doing that. Good test coverage. Too many times I've seen people named Richard go and do some performance improvement and think everything's wonderful, go and show someone else how wonderful the performance is, only to realize the performance was great because I actually skipped a whole lot of processing that should have occurred. So test coverage gives you that safety net. And these days, hopefully, I'm not even going to ask, hopefully we have good test coverage in our applications, or at least enough to have some confidence. And the other thing that we have as a prerequisite is our mindset. The biggest thing from a performance work perspective to have in your mindset is thinking beyond the abstractions. It's really easy with computing, obviously, these days, that we have abstraction after abstraction after abstraction, but all of it all comes down to what's happening on the network and what's happening in the CPU effectively, or what's happening in terms of I/O. And being too abstracted is a problem. Entity Framework, for example, is great in that it lets you interact with databases without having to really think about it. But we've all seen, maybe not all of us, some of us might be perfect, the rest of us have seen really bad results from EF code that has been, EF's doing the right thing, but our usage of it is bad because we didn't understand the abstractions. That said, by the way, .NET 7 coming up recently, next month, coming up recently in the future. Coming up next month has some good improvements from performance around EF itself. They've done some work to try and remove and reduce round tripping to databases for certain types of operations, which is fantastic because we're going to get for most of our applications, a great performance improvement by doing nothing else other than updating to the latest version. It's like, yes, that's my kind of improvement. So there are our things. We are then running a simple loop, which is identify something that matters to our end users. There's no point spending 3 weeks, 4 weeks doing a performance improvement to save 20 milliseconds off an operation that happens once a year. There's not really a return on investment on that. So find something that matters to your users, that has value, baseline your current performance. This is obvious, hopefully. Make the change, assess your performance, rinse and repeat. And we're going to do exactly that. We're going to do this with a library called PDFpig, thus the name of the talk. See what I did there? That's pretty good. Pat on the back for myself. PDFpig is a pretty popular library. It's a port of Apache box, PDF box, as you can see. I'm using version 0.7 because the team that writes or looks after and maintains PDFpig has done their own performance improvements. So I didn't want to take something that was already well optimized and then try and improve that. I wanted to cheat and make it easier for myself. So I've gone back to a previous version. The good things around this and why I'm using it is it's fairly isolated, which is handy for a talk. It's a library, so it's good. And it's got good test suite. So there's good coverage on this. Anyone use this, by the way? I'm curious. Nope. Anyone never heard of it before and now goes, ooh, I'd like to use that. Yeah, okay, there we go, good. All right, you're welcome. And we're going to be using a few tools. I don't want to go too deep into a lot of tooling. I'm going to keep this really simple so that it's something we can all adapt to and use at our work. So PerfView, benchmark.net, I'll put these links up again at the end. SpeedScope, and we're going to look at the .NET source code, believe it or not, because we need to go beyond the abstractions. All right, so we're going to do it. Let's go, Richard. Let's jump across to VS Code. Excellent. All right, so VS Code is awesome for doing C# development. There's going to be talk on that later by a gentleman over here, Mr. Melgi. I don't use the Visual Studio IDE anymore. There's no point. This does everything I need. And I've got, you can see PDFpig and the test library running there. So, wow, this resolution's fantastic, by the way. And I could look at the tests and just to prove that they run, I can run some of those tests and this will do its thing and go, hey, look, there's tests and it works and everything's good. I won't run the entire suite because the integration tests take about 10 minutes and it's probably not a very exciting 10 minutes watching tests run. And I've done what most of us will do first time we go and do any baselining of performance, which is write our own little test wrapper utility thing. Has anyone done this? This code might look familiar. We start the stopwatch, we make some calls and we stop the stopwatch, print the results to screen. Yeah? Who did this last week? Okay, good, all right. All right, so we're going to run this code here and I'm just going to do the classic .NET run config release. Not debug. Don't make the mistake that I have done far too many times of forgetting to put it in release mode. Debug is going to be slower. You haven't got the code optimizations. You're not measuring what your users will see. So run it in release mode, and this is going to do its thing. And cool, it took 7.6 seconds to process a PDF file, figure out there's 838 pages and 198,380 words. Beautiful. I'm in fact going to do the next thing that we all do, which is go to Notepad and go, cool, let me just write that number down. Where did Notepad go? Come back. Come back. There you are. All right, so that is, what did we say, 7.6. 7.6, and I'll just zoom that up. 7.6. Now, what's the problem with what I've just done? Problem is my results are highly inconsistent because I'm running on an operating system. Operating systems are doing other things at the same time. I'm never going to get a pure result. So, liar! Liar! All right, we can cheat, we can make stuff happen, we can do this, and I'm going to be now doing things on the operating system. And, come on, don't make me up. Yes, thank you. Now it takes longer. So now I might have looked at that first result and got an 8.0 and then run the test again and gone 7.6 and gone, yes, I've just shaved 5% off my application without any real understanding that I've actually done nothing at all. we have to do performance work by running the perf test a lot of times and looking for deltas and looking at means and distribution and everything else. We should also make sure that we're running our machine without as few background processes as possible, run it in high performance mode so that you don't have CPU throttling going on under the hood, again, beyond the abstraction and the like. But let's say for the moment that our number, when we average it out, goes to about 7, 8. Is that okay with people? Yeah, you're okay. Okay, good. All right. First thing, improvement-wise, that we're going to do here is I cheated. And I'm running this as a .NET 3.1 app. Just to show you the improvements in a framework, let's change that to 6. Run it again. Anyone want to guess what the numbers are going to be? 4 seconds. Ooh. 5, 7, 12. Who said 12? Me. 6.3. Oh, okay. And we'll run it again. And of course, I'll try my best to make it go slower, just for consistency and fun. And do. And do you want to see the PDF, by the way? We're using Homer's Iliad, which has 838 pages. Thought I'd do a small PDF. Text heavy. What's that? 6.9. So we're definitely getting some performance improvements here, which is a good thing. Simplest performance improvement you can make if you've got old code, update to the latest runtime. You're going to get the benefits. And when 7 comes out, you will get more benefits. There is also a talk later this week talking about the other parts of .NET performance and improvements in general, profile-guided optimization, a whole bunch of other things that are happening in that space, GC improvements and the like. If you're interested in this space, strongly recommend going to that one. I'll be sitting in the back as well. 6.2, 6.9, 6.3, let's say that's a lazy 6.5, for want of a better term. So we've just saved 1.3 seconds by doing nothing else. I'm definitely going to the boss and saying, hey, can I have a pay rise? They might laugh at me, but it doesn't hurt to try. All right, now, that done, let's actually figure out where things are happening. Now, if I look at my code and I want to improve this loop here, I'm opening a document, I'm parsing it, getting some structure, number of pages, then there's a loop. I don't know technically, I do because I've looked at it, but I don't know looking at the code where the performance time is. Where can I save time in this? Is it in the parsing inside PDF document open? Is it in hitting some of these methods? Is it in get words? Is it get page? I can't tell. Some of this could be statically done when the parsing happens and it's a simple property return. It could be much deeper. I could go and look at the code and try and eyeball my way through it. Again, I'm sure none of us have ever done that at all this week. I don't want to do that. I actually want to use a tool to do it for me, which is great. I'm going to profile the code. This is Perfew. I can't make the font any bigger, I'm sorry. So there's going to be a little bit of zoomy going on. It's a technical term, zoomy. I'm going to run a command and it's going to say, hey, Sunshine, you're profiling at the kernel level, you need to elevate. So I will do that. Now, before I show this UI, let me go back to, get out of there and go back to the slides. This is your typical developer-written user interface. And I'm sure we've never done this ourselves as well, right? We like building the shuttle control system and wondering why users don't find it easy to use. There's a few things here. First, we're going to run a command, which is our application, our compiled application. It's in release mode, obviously. Perfew will take, by default, a sample every millisecond. So every millisecond, it will stop execution of what's going on, grab the call stacks of every single process on the system. So it will slow my machine down and record that. And every millisecond does the same thing because we want to see where things are at. So sampling every millisecond. We are also going to capture a few things here. We're going to capture thread time so we can see if there's threading happening in the application. We're going to look at file I/O because I know I'm doing some interaction and I/O is important. And we're going to look at memory allocation to see if we're going to have issues with garbage collector and the like. When we've done this, we are also going to see some output that looks a little like this. So we will see a lot of options in terms of what Perfew captures, which is great. I don't care about most of them for this particular case. We care about the ones that are highlighted, which are CPU stacks, Garbage collection statistics, the thread time, and particularly noting the ready thread one. So this is more where you've got threads that are available to do work and ready to do work, but can't. So they're blocked. And disk I/O. Reasonable? Yes, absolutely. I think that's great. Let's continue, he says, talking to himself. All right. Purview. Turn off thread time. I will just bump this up so it's easier to see, so you can see I'm not lying. I turned off merge because I don't need to share this file anywhere else. Oh, I forgot that one. And run the command. The window disappears and we end up seeing over here that something's working. This is Purview doing its thing. Who's used this tool? Okay. For those who haven't, this is a Microsoft tool. It's very cool. And it's going to spit out some results and open it up. And there we go. Awesome. So here's our CPU stacks, our memory, and disk I/O and thread time. So the first thing I'm going to look at is the garbage collector, GC stats. Now, I want to go to the performance tester one, and I can see here that it's going to give me some numbers, which is fantastic. Let me bump that up just a little more so it's easier to see. Here's our stats of Gen 0, 1, and 2 collections and how long we've paused. And what I see here is that we've made 10 Gen 2 runs, and it's cost us in total 8.3 milliseconds. Is this our performance bottleneck? Cool, so from an investigation detective perspective, we can ignore this. Yeah, we could probably allocate less memory, but it's not our bottleneck. So we need to focus on the things that matter, and it's not that. So noting that, I go, okay, sweet, ignore that. Let's go look at disk I/O. Now, before I do this, you will see a view that looks something like this. Now, I'll zoom it up. Again, developer-built UI. It looks confusing at the start, particularly that thing above the when, which has the asterisks and the letters and the nines and everything else. Purview has inbuilt help, which is good. It's dense. It takes a little bit to read it and understand at times, but it is, like all things with great power comes terrible documentation. But it is really actually pretty good because it will tell me what these dots mean. The dot in this case is that in this time period, this thread, process, method call, whatever it is on the left, consumed between 0 and 0.1% of our total time, or our total metric. And it does 32 buckets across the execution period that we ran for, and just kind of gives us an ASCII version of a little heat chart thingy. Ticker, that's the word I'm after. Which is nice. So when you get used to it, you can eyeball something and go, oh, okay, I'm not interested. That's not my problem. It's in really that one above, which is cool. So let's go back and actually look at the results that we've got in this particular case. So disk I/O stacks. So there is every process on my system. I told you there's everything. So yes, you are correct. There is a lot of processes your operating system is doing in the background and why you get so much inconsistency in terms of how things operate. It's kind of frightening. Kind of cool at the same time. So let's open Performance Tester, which is, sorry about the fact that it keeps moving on me, which is this application here. And looking at this, if I come along and eyeball our metric chart here, what do I see? Disk I/O at the start, probably where we're loading the file up, and not much after that. Is this process I/O bound? Not really. So, cool, we've eliminated another suspect in our investigation, dear Watson. So I can move on from that one. Then I'm going to go to thread time. Let's see if we're blocked on threading. Again, open the performance tester. Cool, and I'm just going to go straight to the name one, which looks like the screenshot I showed earlier. And you'll see now, Purview, when you do this particular view, generates, categorizes threads into pseudo states, indicating if it was blocked, doing some CPU work, doing a hard fault, or something else, and you can see some of them here readied by thread ID and waiting. These are the ones we're interested in. I'll make that a little bit larger just because I like zooming in and making you seasick. Readied by thread ID is basically saying there's a thread that was readied by another thing and it was sitting around and waiting for, in this case, less than a millisecond. Okay. Oops, oh, sorry, that's horrible. Okay, coming back up here, block time. We had 88% block time and 11% CPU time. Are we in trouble here from a threading perspective? It's a trick question. Everyone's going, I don't know how to answer that one. You're the one up the front. All right, turns out not all block time is created equal. If I go back to the call tree, what I see is I have a startup thread and then 10 other threads that have been created by .NET as part of running the process. And if I come across to the right, I can see time is spent on all these, mostly. But what have we got? We've got the background garbage collector, we've got the JIT doing its thing, the TIG compilation workers, JIT stage 1 and 2. We've got the .NET finalizer, probably releasing the file IO, file handle that I created. And then a bunch of other threads that have done a grand total of 1 millisecond of time and almost no processing at all. So if I make those somehow more available, it's not going to help. These threads are blocked because they've got nothing to do, which is why we want the ready time. That's the one that really counts. So what I see here is if I just filter down to my startup thread, and if I right-click and include item, sorry about the zooming there, I wish I could control that better, and go back to by name, I now see CPU time is 99.2% of this application. So what do we need to investigate? CPU time. Yay! Which is exactly the bottom of the stack that I talked about. Ironic, I know. But at least we've done that process of eliminating candidates and working through what's important. So we're in IO, blocking, and then, okay, this is a CPU-bound application. Now, I could start digging into this in a little more detail. And I will. I'm just going to open the CPU stacks for a moment just to have a look at what's going on here. I can see I have the JIT creating arrays and newing things up and getPage doing something or something along those lines. GetPage was one of those methods that we called in our loop. It's the one that's got the most work in here. That's probably our focus. At this point, I can then jump in and try and dig through everything, but I want to isolate the code a little bit more. I want to isolate the performance. I should mention, can you see this one here? NTDLL question mark exclamation and module question mark exclamation question mark. This is basically Perfuse saying, I don't know what symbols you're talking about. You will see things like this. Module CLR JIT. So we've got the module name before the exclamation point, and then a question mark saying we don't have the PDBs and the symbols loaded. If you right-click one of those rows, do look up symbols, Perfuse will go and try and load the symbols from symbol server for the library and then be able to expand that into the particular method, which is handy when you want to look at what's going on inside the framework. Again, going beyond the abstraction. The module question mark, exclamation, what the hell, is effectively saying, I can't tell you what the module name is, and I can't tell you what method in the unknown module name it is. This is typically caused by anonymous methods that are produced or runtime generated code because they're not statically compiled at that point. As long as that's a small percentage, it's not going to affect your overall performance. If it is, you can do things in Perfuse to roll those numbers up into the parent call and basically look at the parent methods, find out where it's happening. We're not going to see a lot of that, so that's more for your information. All right, so I don't want to run this all the time and try and dig through. I'm going to cheat because I can, and I'm going to git reset so that I can move forward and go to git switch step 2. Sorry about the being on the microphone. And load up benchmark.net. Who's used this? Again, it is a freaking awesome tool. it's going to do all the statistical work that I mentioned before. You know how we were taking 8 seconds and I would have had to run it a few times, go, it's about finger in the air, 8.7 seconds to execute. Purview is going to do that for me and do it much better. What I need to do is tell Purview what to benchmark. So I put a benchmark attribute on a method and run it, which is our getPage method that we looked at earlier and went, yeah, this is probably a problem. And I'm going to run it for page number 1, 20, and 50 to see if there's any variation between how far we have to dig through in the PDF file, because maybe each time we ask, we're going back to the start and moving forward. So let's go run that. And we're going to go /benchmarks, and again, .NET run, release mode. Now, you will see a few things happening here. Firstly, there will be 3 runs of the benchmark, one for each of the page numbers that we're getting. Benchmark.net will do some nice things for us. Firstly, it will execute the code a few times to get the JIT to get out of the way. Basically, ask the JIT to do that initial tiered compilation and just say, take this method and make sure it's all sweet. Then it will try and run the test a few times to figure out how many iterations it can do at once to get a reasonable number to work with. So in this case, we've landed on 512 operations. Then it runs those 512 operations a few times as a batch to see that the numbers are stable and that guesswork was correct. And then it runs the actual workload. And it's this actual workload piece where we're doing the numbers. And you can see this time, this is page 20 because it was the second one in the list. Instead of doing 512, we're doing 128. Easy indicator that 20 is going to be slower than 1. And we can see also 6 milliseconds per operation, these sort of numbers coming up. It's going to do its thing, and then it will pop out and run 450. And at the end, once it's all done its magic, we'll be able to compare the results of time per operation and how much memory is consumed. And if you can muck around with the settings in benchmark.net and get other numbers out of it, but it's a very, very nice way of doing things. So rather than doing my manual Richard's crappy performance tester thing, I could have taken that loop, put it inside benchmark.net and run it and got a much more accurate and statistical representation of the work that was occurring. It is important, by the way, to note that with benchmark.net, you need to do something with the return values. Otherwise, the compiler is going to go, hey, you know what? You're not using this. I'm just going to optimize you out when you're doing release mode. And then your benchmarks are like that. It's just fantastic. And again, I've never done that and wondered why my code was so fast. So here we go. Here's our results. Awesome. We have, it's wrapped around a little bit. Let me just zoom that out just a fraction. So the page number 1 took 1.25 milliseconds, page 20, 6.28, page 50, surprisingly less time. Okay, fair enough. And we can see that page 20 somehow managed to trigger some Gen 2 collections, used 3.5 meg of memory, page 50, 3.5 meg, page 1, 800K. Okay, cool. I'm not going to dig into the code. I don't need to understand why. I'm trying to find performance problems. One of the temptations when we're doing this type of work is to start digging into more than we should and losing our focus and then going, what the hell was I doing? I've lost track now. And the discipline part of problem solving is really important here. What it tells me is that page 20 is probably the one we want to focus on in this particular case. So I'm going to go back to benchmark.net and just clear that out and that out. And then I'm going to run this again, but I'm now going to profile the execution for the benchmark of just page 20. So I can do that by doing -p etw, which is cool. This is not going to work because it's going to say, hey, you know what, Richard? You can't do ETW tracing unless you're elevated. I go, yes, you are correct. That's why I prepared earlier. It's like a cooking show here, I think. Here's something I prepared earlier. And I probably want to be in the right folder. Thank you for pointing that out. So we'll run that 20 again. And this time, it's going to run the profiler alongside it so we can see exactly what's happening, where CPU is being allocated within the getPage method to try and find what's occurring. I should probably hit the thing to start it, hey, instead of just waiting and going, why is it not running yet? All right, so it's doing a build. You can see also in terms of the build that we are doing the release mode builds. We're turning off build in parallel, deterministic, optimized, true, making sure everything's all good. Again, these are controllable settings in benchmark.net. And there we go. Here's our pilot coming through. 128 operations per batch, which is good, or per workload, I should say. Warm the workload up, make sure it's all good, and then do the actual run. This will run until benchmark.net decides there's enough statistical consistency, and then we'll stop. If it doesn't find any consistency, it will run up to 100 times and then go, okay, you've had enough. We should stop anyway. It's kind of like when the kids keep asking, can I stay up just a little longer? And you go, all right, no, now let's go to bed. So we're done, which is great, and we have generated a profile in this folder here, which I am now going to go and open in Purview. So if I go up to here and change the folder path to the one we just saw, I've got my benchmark there. I'm going to open that up, double click it. Cool. Now, at this point, I can jump into the CPU stacks. I don't want to do that. You're like, why? Why? Because stuff's been happening. Benchmark.net ran it how many times? I didn't count, actually. It ran it a few times. But when it runs each benchmark, each workload, it creates an event, an ETW event that we can use to see what's going on. So benchmark start and stop is for the entire run. Workload actual start and stop are the things we're interested in. This is after the JIT has done its thing, after it's done the piloting, after it's done everything else. And we can then look at two events, start and stop, and grab the time, right-click that, and go, hey, open the CPU stacks for just this period of time. Now I've narrowed in my investigation to just a single benchmark run, so I have a much better view of what's going on inside the code. And I see here now a few interesting things. I see, yes, get page sucking up all my time. Damn you, get page. Decimal calculations, some core CLR stuff that's occurring, whatever else. But this is a summarized view. There's a grouping that's occurred here. I want to make this less grouped, and sorry about that. Let's go to no grouping. This is the detail of everything that's occurring. This is, instead of going with summarized things and trying to help me focus on just the big picture, I'm going into the weeds now. What is occurring? Transformation matrix multiply, decimals transform, etc. There's some, there's one of those classic, I don't know what the hell this is. There is also a little view in Purview called the flame graph. Now this is fantastic, and look at how horrible that is all at the same time. Let me zoom that out and try using this on anything and trying to figure out what's going on. I don't want to do that. That's not good. So I'm going to take this and save the view as a SpeedScope file. SpeedScope is a nice little utility that exists online that says, hey, you can go and upload performance charts to me and give you a much more flexible, visualized view of what's going on, and I can dig through things and I can highlight time and narrow in on ranges and everything. But if you have a look up the left here, there is a left heavy view, which is going to collapse all the calls that are in the same level of the call stack, shove them to the left, and then try and group the children underneath that, which lets me get a better view of overall time. So if I come down, I see here, there's some work around, this is transformation matrix, transform, and it's taking a PDF point. Overall, this is 29% of our execution. Hopefully you can see that okay. I can zoom it in one more time just to make it bigger. And we also have other methods that are floating around as well. What's also nice is if I just select all the time again, at a certain level, when you click something, you can see, hopefully you can see, it will highlight where else that same method is being called. So I can get a feel for where it is in the call stack and if we're being recursive and the like. So that's cool. But what I see in general is that this is all in transformation matrix multiply. There's a lot of work going on there. So we do what we do, which is at this point go, okay, now we're talking. Let's go to transformation matrix and let's go to the multiply method. All right. And here's our method. That's cool. So we're spending 45% of our time in here. Can I improve this code? Doesn't look like it, right? Welcome to performance work. Think beyond the abstraction. What we're doing here, and when you understand how PDFs work a little bit more, is that PDFs are basically, to parse them, we have coordinate systems and we're trying to figure out where things are on a page. PDFs are rendered as effectively pictures. It's how they work. And to work out where a word is and to do a word count, you have to kind of go, hey, there's letters and all these letters are near each other and they all fit within a bounding box. And to work out the bounding box, you need a coordinate system. And to be accurate, the developers built this with decimals so that we can be really accurate around where our box is. Anyone know what gaming engines use all the time? They use decimals, right? No, because decimals suck. Decimals are great for finance. We want accuracy in our currency. Not really useful when you're doing geometry, or not as good. Because what's the difference between this shape and this shape? Which is the difference between a decimal and a float? Nothing at all. In fact, let's go and prove this. Ooh, not that one, Richard, this one. And I mentioned before we were going to look at the .NET source code. So let's go to source, source.net, and look at the implementation beyond the abstraction of a decimal. All right, here we go. Here's your decimal. And let's go look at operator asterisk, which is, we know, is our multiplication. That's really awesome. There you go. Operator asterisk calls another method to do variable decimal multiplication. Excellent. Anyone know what that does under the hood? No, because you've never looked and neither had I before this. Here it is. We are on line 1323. This will do your head in. I'll just scroll slowly. I'll tell you when we hit the bottom. We're not there yet. Are we there yet? Are we there yet? Oh, look at that comment. 192-bit results. What the? Okay, well, we're still going, by the way. And we're still going, and oh, there we are. No, wait, no, we're not. Oh, damn it. Oh, look, there's go-tos. Love it. And then finally we get down to 1518, and that's the end of our multiplication method. Shall we have a look at double for a comparison? All right, I'll start scrolling and I'll tell you when we stop. All right, we stopped. What are we doing with doubles when we multiply? We're effectively putting two operands into registers and asking the CPU to multiply them, and job done, end of story. Because CPUs love floating point numbers. They will deal with them all day long. Decimals are an abstraction over the top of integers. Painful. Extra compute time. So we want to improve our performance. Do we need the accuracy of a decimal? This is where tests are important. I've got a test suite. I can make some changes and verify the test still works. So let's make that change. And when I say make that change, let's actually jump to the branch. All right, and what I'm going to do here is go to step 3. In the code, I've now built, in my benchmarks, a new benchmark using PDF point. This is one of those smaller classes that, if we have a look at it, is effectively an X and Y coordinate as a decimal and an X and Y coordinate as a double. I create a new version of that. So I can compare the decimal implementation with the double implementation and do some operations on it to see how it runs. This is fun. I like doing this. It's great. So now we're going to run our benchmark, and I'm going to run our PDF point one, number 1 this time. just to compare two different implementations of exactly the same code, changing just the types. Anyone want to have a guess of how much faster this will be? Given you saw the 300 lines or whatever it was of code. It's going to be at least 1%, right? Oh, all right, so I think this is the decimal one running first. I can't tell you, but you can see how many operations are in each workload. 67 million, is that the number? 67 million? That's cool. That's a good number. All right, do your thing, do your thing, do your thing. I'll just sing to myself. Do you want me to tell some dad jokes while this is running? I was going to say tell some bad dad jokes, but there are no bad dad jokes, just so you know. And how many operations for this one? 536 million operations. I'm guessing this one's going to be a little bit faster. All right. Come on, baby. You can do it. How many workload actuals before we stop? 18? Do I hear 20? Do I hear 25? This is always part of the fun, right? When will this finish? 4 hours later. Come on. 38. All right. Look at the difference. Because we went beyond the abstraction, we focused on an area, we went through the loop, we measured, we baselined, we changed to verify things. Now, this is a very discrete piece of work that we're doing here. This is not necessarily something that will work across the entire application. But I can see that by simply, for this method, moving from decimals to doubles for this point, improved performance by, I can't even do that as a percentage. It's now 0.6% of the time it took before. Now, that's freaking awesome. Let's go one step further and apply it across the entire code base, shall we? Where relevant. Now, it should only be for geometries. There are certain other numbers that make sense as decimals, and if we change them to floats, are going to cause bugs. Probably don't want to do that. So we do need to be careful, which is, again, why it's important to have that test suite there. So let's git switch to step 4. And in this case, I've now gone, and behind the scenes, you'll see that I've added things for the transformation matrix. I had a decimal and a double implementation, and I changed things around, and I've moved it all about and everything else, which I'm not going to run through with you. What I am going to do is go back to our low ball quality performance tester application, just to go finger in the air, the entire operation, roughly how much has it improved? Guesses? No guesses. 2,000 times. If only that were true. All right, let's run release mode. Now you can tell that I've made changes because I haven't cleaned up the compiler warnings. Welcome to Richard's Development Technique 101. If you can't see that, maybe you can see that. In fact, let's do it without the run, bin release, net6, performance tester dot exe. So we had 4.4, 4.1, 4. Hopefully 4, 2. So roughly what now? 4.2, 4.3, something like that. 4.2, we okay with that number? Pretend that I've run this 98 times and I've run the JIT and I've done all the other stuff that benchmark.net does beautifully. All right, so let's go to our notepad where we had our rough numbers before. And we are now at 4.3 seconds. So from our starting point of .NET Core 3.1, which was a cheating start point, I get it, I'm going to say, I'm claiming it anyway, that we got almost a 50%, well, 40% improvement, something like that. We've saved 3.5 seconds. Not bad for 1 hour's work. Wasn't 1 hour's work, just pretend. But even from our .NET 6 code, we have saved over 2 seconds. So there's a 30% improvement for the same runtime. simply because we went through that process of having the tests, thinking beyond the surface level, baseline, change, baseline again. Now, when I was preparing this talk, I did do the good thing of making performance worse through some of the changes I was trying. Again, this is why the baselining is there, because you want to know that when you've made the change, it has made a difference, a positive difference. So coming back to our slides. So detective work with puzzle solving. We went, we identified, we baselined, we came, we saw, we conquered. It was fantastic. Then we went home and watched Netflix. The tools we used, PerfView, benchmark.net, SpeedScope to visualize that flame graph in a better way. That's not something you have to do, but these are all free tools, which is great. And going beyond the surface at times for the .NET source code. Now, you might, in some of your applications, not be going to .NET source code, but going into third-party libraries. With most of our things being on NuGet, a lot of our dependencies on NuGet and open source these days, being able to dig into third-party libraries is a normal part of development. You should, and I would encourage you to do that. With the Microsoft source code, it's all open as well. You know, .NET code's out there and invisible in the public. You might not want to dive into that given what we saw. Leave that for others and just understand the framework's good, but at times you might want to go and have a look and see what it's doing under the hood. And again, investigate beyond just what your code does. It's really easy to look at a line of code and go, this looks pretty simple, and move on. I did that with what we looked at today, the first time I ran through it. Okay, there's some matrix numbers, okay, fine, move on. And it wasn't until I stepped back, paused, and went, hang on, why are we using decimals? Where's the value? And I went, beyond the surface level. All right, and at that point, we are done. I even finished early because it's a performance talk. Bad jokes aside. That's it. In terms of a talk, we're done now. Go back to work or go enjoy the rest of the conference or ask questions. I'm open for questions. Yo.
What's been your experience with assisting more junior developers with upskilling?
Okay, so the question, what's the experience like upskilling junior developers with this? Pair programming, more than anything else. I mentioned before the over-threading problem. That was someone who had less experience in the industry, and the way I helped them through that was to walk through and literally do something like this as an example of the process and just show them by example, step by step. It does take time, but you know, it's the classic teach someone to fish versus do the fishing for them. And so they can then take that and apply it themselves afterwards. So just look for those opportunities and see how it goes from there. Good question. Other ones? Up the back and behind the spotlight that I can't see?
I don't know. Is PerfView for Mac?
Is PerfView for Mac? PerfView is available for Linux, at least the gathering of data. Actually, I'll show you here. We'll just go to github.com/Microsoft/PerfView. And it's .NET Core, so you can jump in and get PerfView and Trace Event, which are all built in. That's downloadable and run it. Previous versions, .NET PerfView 2, Trace Event was separate, so if you're running in Linux, you had to go and run Trace Event to do the capture separately and bring it back to Windows to analyze. I'm pretty sure 3 is now runnable on Mac and Linux and everything else because it's a .NET Core program and uses WPF, maybe? I haven't looked at that part of the source code. But yeah, should be okay. Other questions over here?
Yeah, so in the example you showed us with the decimals versus double source code in .NET, so what happens if you come across a piece of code that you need to improve? Like you figured out that that's the problem with that piece of code, and you look at it and it's not obvious to you how to make it do less. So what's the process then? How do you go about finding things to change?
That's the how do you go beyond the surface level question. So the question, just to repeat, is if I find something that I think needs to be improved, but I'm not sure how to improve it, what do I do? What do most people do in that situation? you start exploring, you start trying things, and this is where that baselining and remeasuring becomes really important. So it might take you a few iterations to play around with it and go, oh, I don't know, for example, I'm doing string manipulation. Do I want to turn this from a string into a span and then do some work across spans, for example, or use a memory of type T kind of construct? Only one way to find out. Try it, see if it works or not. The other thing you can do is look up the tree. So it's not always what's below, it's what you're being called from. And maybe you're being called too many times from parent code. So again, something like the flame graph, you might see that there are lots of callers coming into the same method and that your method is spread everywhere. So maybe it's a case of collating that and doing a work in batch somewhere else, or pre-computing things and changing some of your application design so that you're not as chatty, particularly for network calls and the like. There's no real guidance I can give you other than to try stuff, but think more about the problem overall, not just the specifics. So you will go deep and you will also go up in terms of most work. Other questions? Yep.
Yeah, you showed basically a simple X here where you're running these tools.
Yep.
If you're applying it to something like microservices or something like that,
yep.
Have you done that and how do you go about it?
So yes, though some of the tools you'll use, microservices, are going to be, you're looking at the network calls. So in the profiler,
even if you're running it in like on your machine.
Yep. Sorry.
You know, it's sitting there waiting for work to do. How do you go about using those tools? Probably a test framework or something like that?
Oh, for a single service?
Yeah.
So the question, just for those who didn't hear, is what do we do in a microservices situation? So if we're doing a single service, it's effectively an executable.
Yeah.
So you might want to abstract away network calls, have mock implementations. If you are running in Kubernetes, there's a tool we use internally called telepresence, where we can actually have our app or our microservices deployed to a cluster, and using telepresence run one service locally and basically proxy network traffic to my local machine and back up. So I can run a full environment with just one service on my local machine and do work around that. So that, if that's of value, telepresence.io, this cool thing here, that's, yep, well, they changed the website. That's effectively this. I'll just quiet. We're going way off track here, but that's okay. I don't mind doing that. Is it this one? One of these, architecture, something. Load the page. No, that's intercepts. Anyway, effectively this tool will, as I said, do proxying to and from your local machine. So you can then attach to your local machine. You don't even have to run it in a container. You can actually run a local process and have the traffic intercepted going to and from, which is just fantastic. Needs a bit of setup. You've got to have some, obviously, updates on the cluster to put in the interceptor. Don't do it in production. But that could work. Alternatively, you try and run containers or mock services or something so you can isolate, but yeah. Final question from anyone? I can't see if you're over there, but that's okay. All right, well in that case, ladies and gentlemen, thank you very much. Go enjoy NDC and I will talk to you soon.